So hello everybody, we are dealing with a very interesting problem today, and it is going to deal with a lot of concepts. So mainly the concept is based on work power energy and it is based on particle dynamics aspect. So let's get started with the problem. The problem is stating a massive homogeneous rope of length L is suspended between the two nails A and B driven in the same horizontal level. The rope makes an angle theta with the horizontal at the nails and its lowest point is at a depth d below the nails. A bead threaded in the rope released from the nail A slides down the rope without friction. If the bead is so light that the shape of the rope remains unaffected, then find acceleration of the bead as it passes the lowest point of the rope. So let me take you through the problem. I am giving you a hint. Post seeing the hint, maybe you can give it a try yourself, and then if you are unable to get a particular solution, you can continue watching this video. So let's get started. We will first of all draw the scenario again which is stated in the problem. So this is the scenario that is stated in the problem, and now as we start solving it, the first thing to note over here is that the rope is said to be massive and homogeneous in nature. So the word massive in itself is stating that the length of the rope or the size of the rope is too big compared to the size of the bead. And then it is also said that the bead is so light that the shape of the rope remains unaffected. And then we have to calculate the acceleration of the bead as it passes the lowest point of the rope. So when the bead is released at this point and it is not offering any friction in the trajectory of the bead, then as the bead reaches the lowest point over here, which we mark as point M. So at this point M, the bead will have a certain value of speed or velocity, due to which a component of acceleration v square upon r will act. And we are looking for that particular acceleration where we can calculate for v square upon r. Now the next problem or the next hurdle which we have in this problem is that the shape of this rope is not mentioned. It is not mentioned if it is in the shape of a circular path or any other shape is not mentioned in the problem. So we need to think in terms of calculation of radius of curvature at the point M. So by means of radius of curvature, I mean to say that if we draw a large number of circles, then at this point M, if we draw this circle over here, it will be of a certain radius. Let us say radius of this circular path is RC. So we need V square upon RC to solve this particular problem. So this is the entire idea which we will be using in this problem as we solve it. So now in case you want to give it a pause and think about the solution to this problem, you can do so, or otherwise continue watching to know the solution. So we start by applying work energy theorem or energy conservation theorem as the bead slides from point A to M and there is no change in the shape of the thread or rope is taking place. So we can say that total energy at point A is equal to total energy at point M. So total energy at A can be written as mgd, where we say d is the height above which the bead is released, and at this point it is going to have some speed v, so we write it as half mv square. And from here if we calculate v, so we write v is equal to 2gd and then we place a square root. So this is the first part of the equation that we have, or the first equation for this problem which we have. And the acceleration at the lowest point M which we wish to calculate is am, or acceleration at the point M is going to be v square upon radius of curvature at this point RC. So now the entire length of the problem is going to be spent on calculation of this RC, as we already know this value of v square which is equal to 2gd, and then we don't know anything about this RC. So the entire length of the problem is going to be to solve for this value RC which we have. So now in order to solve for RC, let us come back to this diagram. So if we look at this particular diagram, so over here we can say that if at this point where M is the point of contact, if we consider a patch which is like this, and if we construct two lines of normal at this point, so these are the two normals at this point, and this normal is subtending a certain angle which we say as delta theta, and then we can bisect this delta theta into two halves, delta theta by 2 and delta theta by 2. So over here at this point there is a tension in the thread which we are referring as tension at point M Tm. Similarly, the tension at this point is also equal to Tm, and then Tm is going to have two components. So based on this aspect that this value is equal to delta theta by 2, so if we construct a triangle like this, so we can say that each half is going to have delta theta by 2 and the other half is delta theta by 2, and the total angle is delta theta. So over here if we are considering a line like this, so we can say that if this is delta theta by 2, this is 90 degree, so 90 minus delta theta by 2, again this angle is 90 degree, and then we will again land up with delta theta by 2 on this side. I am repeating it again. So if we draw a line like this, this will be 90 degree, this one will become 90 minus delta theta by 2. If this is 90 degree on the line of tangential line, then this will again become delta theta by 2, and similarly on this side it will be delta theta by 2. So now over here we can say that this component will become Tm cos delta theta by 2. Similarly this one will become Tm cos delta theta by 2, and on the other side we will be having Tm sin delta theta by 2. So we can say that 2Tm sin delta theta by 2 is equal to the value of this weight of this elemental part which we have. So this elemental part is having a certain mass, which we can say that if the total arc length can be calculated as delta theta equal to arc length upon radius. So we can say that the arc length is equal to r delta theta, and therefore if we are considering that mass per unit length as lambda, so mass per unit length m by L is equal to dm by r delta theta. So from here we can say that dm is equal to lambda r delta theta. So if we consider dm as lambda r delta theta, so we can say 2t sine of delta theta by 2 is equal to dm times of g, and therefore we can say 2tm sine delta theta by 2 can be written as delta theta by 2 is equal to dm. So for dm we are writing it as lambda r delta theta into g. So this is the aspect which we have, and then on solving we can write that Tm is going to be lambda r, where r is also equal to rc times g. So this we are referring as, so the first one which we referred as the equation 1. So this one, let us refer this one as equation number 2 which we have. So we are writing this one as equation 3 which we have. So this one is equation 3 which we have. So now the next problem which we have is that we don't know the value of Tm. Otherwise we can write r, where r is equal to rc in terms of Tm. So if we write r in terms of Tm, then we can write it as r is equal to Tm by lambda g, and the problem is over here. If we write the value of Tm, so Tm by g, so the problem will solve over here itself, but unfortunately we don't know this value of Tm. So now we will try to calculate Tm in terms of the data which is given to us. So to calculate Tm, we are solving this rope system which is hanging from the 2 points A and B. I have already solved one of the problem where I have explained how to calculate this Tm some days back in the channel. I am just pinning that video in case you remember watching it, then this problem is over for you. you can calculate the value of Tm and then substitute the value and get your answer. So I'm showing it again over here. So at this point A, we can say that if tension is T, so since the diagram is symmetrical, so tension is also T on this side of the thread. And now if this angle is delta theta, so we will be having two components, one in this direction. So we will be having a tension T in this direction, a component of T in this vertical direction, and then a component over here in this direction. So if this is T and this angle will become theta, so this is going to be T sine theta, and this is going to be T cos theta. So similarly on this side of the rope we will have this one as T cos theta, and this is equal to T sine theta. So 2T sine theta is equal to weight mg in the downward direction, and since we are writing W mass in terms of lambda, so we can write it as lambda Lg, where L is the total length of this massive rope which is mentioned, and this will become equation A, let us say. And similarly over here we can say that T cos theta will cancel each other out, and at this point if the tension in the thread is Tm, so this Tm or tension at any point in this thread in the x direction, if we call this one as x direction, so Tm at any point on this thread is going to be T cos theta, because there is no component of force in the x direction present at all. So since there is no component, so tension at every point will be same. It is just like solving a problem like this. I am just taking an example to make you understand better. So if we will be having two people playing tug of war, and if they both are pulling this with a force of 50 Newton each, so if they are pulling this with a force of 50 Newton each, then tension at any point on this thread is going to be 50 Newton, because net force is equal to 0 on in the x-axis direction. So at any point if we are breaking this rope and trying to find by drawing an FBD, so 50 is in the towards left direction, so 50 must be on the right, or 50 is on the right direction, then tension in the thread must be 50 on the left side at any point on this thread. So using this idea we are saying that Tm is equal to T cos theta. So now over here if we substitute the value of T, where T is equal to lambda Lg by sine theta, lambda Lg by 2 sine theta, and then we will have another term cos theta. So over here we can say that Tm is equal to lambda Lg by twice of tan theta, and this is going to become equation B which we have. So now if we go back to this part which we have solved, so Tm is equal to lambda Rg, so we are just using this expression over here, that Tm is also equal to lambda Rg. So lambda Rg is equal to lambda Lg upon twice of tan theta. So from here we can put the value to obtain the value of R. So R can be written as, so we can cancel out G and lambda. So from here we get R as L upon 2 tan theta. So this is one thing which we needed the whole time. So in terms of L, 2 and theta which is given in the problem, so length L is given in the problem, theta is given in the problem. So we have written this in terms of this. So A can be written as 2GD by RC. So 2GD by RC. So acceleration at point M which is equal to 2GD by RC can be written as 2GD by L into 2 tan theta, and therefore we say that acceleration M is equal to 4GD tan theta upon L. So this is the final answer for this particular problem which we are solving. So one of the finest problems which we have. So most of the time when a question like this is asked, they end up asking the tension in the thread. So tension in the thread must be known to you. The problem is in circulation for a long time, and then this one we solved for calculation of acceleration of the bead when it is passing the lowest point of the rope. So we have solved something new. I hope you like the problem. Continue to watch the channel for more such troublesome videos. Do like, share and subscribe the channel for this content. Continue learning. Take care.